Okay, geographers, this is your lab 10, I think, right? I know, I'm pretty sure that's what the number is. I don't know, it's this one. Whenever this one pops up, that's the number. And you can see, stole this one. Borrowing. Let's say borrowing, simply because we're not in class together. We can't be playing around with the actual rock samples and all that stuff. So this works for some stuff. And what this lab is all about, it's geologic dating, okay? Meaning how old is the stuff we're looking at, right? Taking rocks and trying to figure out when they formed. And we have two ways of doing this. We have what's called relative dating, which is where we put stuff in order. Okay, so we can say, all right, so this rock over here, this formed first, meaning it's the oldest, right? Then this one formed, then this one formed. So we put things in order from oldest to youngest. Okay, that's relative dating. And to be able to do that, it requires some logic, some basic logical reasoning about how it would have to be. All right, we figured out some rules, some principles that help us figure out, oh yeah, this one has to be the oldest because it's logical, basically. And I get into that again. I'm going to push you over to the lecture class videos if you haven't yet looked at that stuff. Check out the one on historical geology, where I spend time on dating in there. I think it's in the middle, toward the end of that lecture. But I explain the difference between relative dating and absolute dating, which is the other type. And I also go into these specific principles, or at least a few that are going to help you with this lab. So there's the principle of original horizontality, okay, and that's effectively saying that rocks like sedimentary rocks, they originally form horizontally, meaning they're flat. Okay? These three right here, conglomerate, sandstone, shale, limestone, those are all types of sedimentary rocks, which I'm sure you all know, being champions of Lab 9 or whatever the one was before this one, right? Learning about physical geology and all that. But it's the idea that all of these would have initially formed in this flat horizontal way. Okay? Then there's the principle of superposition, which is simply arguing that the layer on the bottom is older than the one above it. Okay? Or another way to think about it is, as you dig down, you're digging back in time, all right, or going back in time. Okay? So, and I go into this in more detail in that lecture and show you how these things work. There's the principle of cross-cutting relationships, where you've got, a rock that's cutting through another rock has to be younger than the rock through which it cuts, right? Because if you think about it, that rock couldn't cut through something that isn't already there, right? So that's an example. I'll point out in here too a few things like this wavy line in there. It's what we call an unconformity. And in effect, what it's showing is that through the years, this wavy part, that was the surface, that was the Earth's crust, that was the ground, however you want to think about it. And it was exposed to the elements and weathering and erosion. So some of it eroded away, and that's why we have little dips in there. So you can think of this, however long ago, and that's the thing with relative dating. We don't know, based on that, if this stuff formed, 100,000 years ago or 1,000,000 years ago or whatever. We're just going for order, right? But before A and B exist, C right there was the top layer. And then through weathering and erosion and stuff we'll get into with the geomorphology talk later on in the lecture class, we have stuff eroded. So think of it as like these are hills and valleys right there. Okay, and then later, through other processes, through geologic processes, B forms, and then A forms, right? So that's what an unconformity is. This line right here, it's a fault, meaning a break in the rock. And I don't think I talk too much about faults in the lecture class because we're trying to streamline this stuff. But that's what this means. Yeah, so you can see like P and P, it was all the same rock, but with enough pressure and stress and all of that, the thing snapped. And that's what a fault is. Okay, so with all this stuff on this first page, what you're doing is you're putting stuff in order. You're saying this is the oldest, then this formed, then this happened, and so everything is just going to be in order. Okay? Listen to that discussion of relative dating, that video lecture. Take your time with it. Just think logically, and this shouldn't be that hard to do. Right? Says the guy who already knows how to do it. I mean, it might. Some of these you might pause a little bit, but just remember, just think. There's no trick to it other than just thinking logically, like the example of, something can't cut through something that isn't already there, right? Think about what has to form first before the other thing can form. All right, so that's how this whole relative dating thing works. And on the second page here, we have what's known as the principle of fossil succession, which is something I actually skipped through. I think I show a slide and I skipped through it in the video lecture, but it's a useful one. It's what you're going to use in here. And it's the idea that we can use similar fossils in different parts of, the world. Like here we have Arizona and we have Utah. Okay, so these areas separated by miles, but we have the same fossils. And so it's the idea, like we have this triangle right here, indicates one species of creature that is fossilized in this limestone, and that's in Arizona. And then we see here, we have the triangles in limestone, same species, right? And so that would indicate that really this right here is the exact same age as this right here, right? Because it's got the same organisms as well as it's the same rock itself, right? So what you're doing is you're linking this stuff and trying to get a picture, and so you can get a sense that, it's that whole principle of superposition, the idea of, digging down, going back in time. That's all well and good. But what we see is that even if it's at different layers in the earth, like imagine this is a cross section, right? This is the ground today, right here in Utah. This is the ground in Arizona. What we're seeing is that the upper ground in Utah would be much younger than the ground in Arizona, right? Just in the sense that that limestone there is the exact same age as this limestone there. Okay, hopefully that made sense. Hopefully that didn't make it worse, but that's the idea. So that's what this whole fossil part is you're trying to figure out how these separate rocks in separate areas here are connected in terms of that relative timeline. Okay, so that's how that works. Then on the next page, you're going to get into absolute dating, which is where we try to get an actual number. Right? We're not looking for, order, first this, then that, whatever. We want to say, no, this was 100 million years ago, or this was 20 million years ago, or whatever the number might be, right? So an absolute date is where we can say exactly how many years ago this thing formed. Okay? And it can be fuzzy. So like absolute sounds like exact. We can get some good numbers, but we also, you'll see, well, I explain it in the lecture class. So you can have some stuff where it's kind of, between this and that, but as long as we're getting that number, that's an absolute date. Okay, so order, first, second, third, that's relative dating, some kind of number, this many millions of years ago, or billions of years ago, or whatever, that's absolute dating. Okay? Now the idea, and I explain this at the end of that historical geology lecture, but the idea, what we're doing here, it's radiometric dating. It's using these radioactive isotopes and their decay to calculate exactly how long ago this rock formed. All right? do yourself a favor before you get in here, because this doesn't fully explain it, but watch that lecture. Okay? If that's not enough, I'm sure you can find on YouTube some, detailed stuff on how half-lives and radioactive decay and this kind of radiometric dating, how that works. Okay? And carbon, what it's showing here too, so it's like carbon 14 is this unstable element. That's the radioactive thing. As it decays, it's losing subatomic particles, and so by definition, it's turning into a new element through that decay process. So carbon 14 turns into nitrogen 14. Okay? Potassium 40, as it decays, it turns into a new element, argon 40. Okay? And so on. We have a bunch of different pairs of this stuff. So these are, and then the uranium 206 or 238, lead 206 relationship. That's another one that you're going to use through here. Okay? It doesn't really matter the actual elements. This is more about thinking about the process, right? And then it explains what they're used for. Things that were once alive and retain their original carbon molecules. These other ones were great for volcanic rocks, and it gives you the age limits. Okay, so once you understand the concept of radiometric dating and half-lives and how this stuff works, then work through here, and you're gonna be doing kind of logical stuff here. I'm thinking we have more of these arguing students about saying specific things, and you have to determine which one's the which one is the good student, right? Who's the winner of the student competition? Yeah. All right. So that's how that works, and as you go through, and you start messing around with this stuff, you're gonna kind of play together with relative and absolute dating. Okay. Again, you're simply trying to logically get some answers here. Okay, so just read through this, do this in the order which I have it set up. I think the page numbers, yeah, actually they had you do it differently in the book from which I borrowed these, but I think this is a better way to go through it. So go through it in this order. Watch that other video lecture stuff, and as you go through, just remember, you're simply thinking logically about this stuff. And if you can just do that, if you can pause and just kind of use that, think of it maybe as common sense, right? Like what has to happen in order for this other stuff to happen? And if you do that, you're going to be set. All right, geographers, good luck. I'll talk to you later.